Okay, so now let's consider composition methods, but where you allow yourself to compose both the underlying one-step method as well as its adjoint. Okay, so we look at composition with the adjoint method. And again, it's like, as I sort of alluded to before, the motivation to do this is to relax. It's like the sort of solvability. It's like for the step sizes, which allows you to solve this for real valued step sizes, even for basically underlying one-step methods which are odd order. Okay, so if we consider a more general composition formula, right, which looks like the following, right? So you can look at the composition method, which is the composition of the underlying one-step method with its adjoint, and then you sort of keep doing this, okay, and then so there's a pair of sequences. It's like of step sizes. It's like the alphas correspond to the step sizes for the underlying one-step method, and the betas correspond to the subsizes for the adjoint. Okay, so if you consider a general composition formula where the original one-step method is order P, right? Then the composition is order P plus 1 if the following conditions hold, right? So, as before, you need that the sum of the alpha i's, sort of all the steps, it's like sum up to 1. Okay, so this goes from I equals 1 to S. And then the other condition has to do with, again, this vanishing of the coefficient for the leading order error term. Okay, and if you recall, it's like there is a relationship. There was this sum of alpha I to the P plus 1, right? But then it's like the beta i's, right, because they correspond to the adjoint, have this factor of minus 1 to the P in front of them. And that comes from the relationship between the leading order error term of a underlying one-step method and its adjoint. Okay, so in any case, you have a condition like this. Again, this goes from I equals 1 to S, and this has to vanish. Okay, so these are the sort of the conditions on the alphas and betas which are necessary to take a underlying one-step method of order P and then construct a composition method. I should say that that's the adjoint, right? A composition method which sort of alternates between the one-step method, the adjoint, the one-step method, the adjoint, the one-step method, the adjoint, and so on. Okay. In order to take then this kind of more general composition formula and have it that it has order P plus 1. So the advantage, if you will, of considering this more general class of composition formulas is that you can get an order increase even if P is odd. Okay, so this allows an order increase even if P is odd. And that was, if you recall, not possible if you were simply looking at the composition of just the underlying one-step method, and you would not be able to basically solve the constraints, it's like on the step sizes while still getting real valued solutions, it's like to the step sizes. So let's look at an example of this. Okay. So let's look at alpha 1 is equal to beta 1 is equal to 1/2. Okay, and you can check that, and you have P equals S equals 1. Okay, and you can check that these conditions, it's like this family of coefficients satisfies this condition, right? Okay, so it satisfies the above. All right, so as such, what this means is that given a first order one-step method, right, psi of h, okay, you can look at this composition, which is a half step of the one-step method composed with a half step of the adjoint, okay? And this is a sort of second order method. You can also check that this method actually is symmetric. It is also symmetric. And it has to do with the fact that if you take the adjoint of this, you think of this as the adjoint of the composition, all right? And when you take the adjoint of the composition, what you do is that you reorder, it's like these things, and then you take the adjoint of each term, okay? So what that is then is that now you have, you know, phi h over 2, it's like adjoint, but then you take the adjoint again, composed with phi h over 2 adjoint. But the adjoint of the adjoint is itself, all right? So this is just phi h over 2 composed with phi h over 2 star, which is the method itself. So again, it's easy to convince yourself that this method is self-adjoint or symmetric, okay? But in any case, it's like, you know, you can easily check that this satisfies the conditions. It's like for a composition formula involving a one-step method and its adjoint to have actually one higher order, which is second order. But again, the observation that this kind of composition, right, gives you a self-adjoint method also sort of tells you that, you know, if the original method was first order, that it actually, this composition has to be second order accurate, okay? All right. I guess I should also mention that, you know, if you take the composition of these things and it satisfies this first condition, then it would have at least the same order of accuracy, right? So this condition is just a condition which guarantees that the composition has the same order of accuracy. Then this second condition guarantees that it has actually one higher order accuracy. Okay. All right. So we verified that this actually is a symmetric method. So let's look at a bunch of examples now. So, example, if if your underlying one-step method is the explicit Euler method, then this composition method, right, is the implicit midpoint rule. Okay, and if the underlying one-step method is the implicit Euler method, and the composition is the trapezoidal rule. Okay, and then another observation is that if the underlying method is what is called the symplectic Euler method, which is an example of a partitioned Runge-Kutta method, right? So it's written, it sort of looks slightly different depending on whether you have the U or V variables, okay? All right. Right, so if you look at this symplectic Euler method, and again you do this kind of symmetric composition, then the resulting symmetric composition method is the Sturmer-Verlet method. Okay. All right. So let me just stop there for now.